Now talking about different powers of iota. Now again, we know that iota is equals to root under minus 1. And if we square iota, what do we get? We are going to get minus 1. The square root would simply be removed. And if I cube it, I would simply get I square into I. So I square is minus 1. So it would become minus iota. So I to the power 4 can be simply written as 1. Now from here, what is the conclusion that we can make is that, let's say if I have I to the power 5, again it can be written as I to the power 4 into iota. So basically it would become iota. Then I to the power 6, this can be written as I to the power 4 into I square. So I square. So basically this would become minus iota, sorry, this would become minus 1. Then again this would go on up till we have any n number of, let's say, powers. So from here, one conclusion that we can make from this powers is that I to the power 4n is always equals to 1. I to the power 4n plus 1, this would always be equals to iota. I to the power 4n plus 2, this would always be equal to minus 1, and I to the power 4n plus 3, this would always be equal to minus iota. So I hope you are understanding how we are writing this. Of course, if you start squaring, that means 4 consecutive powers would have the values as 1, iota, minus 1 and minus iota. Now what if I sum all these 4 values? Of course, the sum of all these 4 values would be equal to 0. That means you must remember this thing, that sum of 4 consecutive powers of iota would always give us 0. Now one more thing that you must remember about iota is that always try to keep in your questions iota to be in the numerator. Let's say if iota is in the denominator, then it would become very difficult for us to solve that question. So what we do is we try to multiply the numerator and denominator by iota, but the only thing is that our motive is to remove the iota from the denominator. So the exact point has been written here in E. To simplify I to the power minus m, where m belongs to n, rewrite I to the power minus m by using its reciprocal and ensure there is no iota in the denominator. Let's say, let me take for an example, m is equals to 1. So I would have 1 by iota. So again, having an iota in the denominator is not preferred, because I wouldn't be able to solve my questions, right? Because I cannot visualize this function basically. So what I'll do is I multiply the numerator and denominator by iota. So from here what I'll get iota by iota square. And what is my iota square? Basically simply minus 1. So this is minus iota. So I've successfully converted my value of iota in the denominator to numerator. Now let's say if I would have 1 plus iota upon 1 minus iota. Again, it is important for me to remove the iota from the denominator. So what I'll do is I'll simply multiply 1 plus iota in the numerator as well as denominator. Now why did I choose 1 plus iota? Because of course this is the conjugate of 1 minus iota, and I hope you all remember we had studied about conjugates in irrational terms. Let's say I have 3 plus root 2. So this is the positive conjugate. What would be my negative conjugate? It would become 3 minus root 2. These two are basically considered to be conjugate. So similarly here, instead of root 2 I have iota. So use these values. So what would this become? This would become 1 plus iota square plus 2 iota upon 1 minus iota square. So basically this iota square is nothing but minus 1. So 1 and minus 1 would cancel out amongst each other. I would be left with 2 iota by 2. So this is iota. Again, I've successfully removed the iota function from the denominator. So keep this thing in mind, that always whenever you see an iota in the denominator, it is your duty to first remove the iota from the denominator and then solve your question further. Again, the same things which I mentioned in the previous slide have been shown here. I to the power 4n would become 1, 4n plus 1 would become iota, 4n plus 2 would be minus 1, and 4n plus 3 is minus iota. And any 4 consecutive powers of I when added always gives us zeros. This value is always equals to 0. Let us look at this question. If alpha beta be the roots of this equation, then the least value of n for which alpha by beta is equals to 1. So alpha beta are the roots of this equation, and if we try to find the discriminant of this quadratic equation, of course it is going to come out to be negative. That means we are going to have imaginary roots. Now of course solving imaginary roots is not difficult for us, right? Because we know our iota function. So let us try to solve this quadratic equation and find out our roots. So what would be the solution of this quadratic equation? Minus b plus minus root under b square minus 4ac upon 2a. So here this becomes 2 plus minus root under minus 4 upon 2. So basically this, now this root under minus 4, what can we write down our root under minus 4 as? Root under minus 1 into 4. So this would become 2 times of root under minus 1, which is nothing but 2 iota. So this becomes 2 plus minus 2 iota by 2, which is nothing but 1 plus minus iota. So these are basically my roots of this equation, and as per the question they had told us that the roots are alpha and beta. That means I've gotten my alpha as 1 plus iota, I've gotten my beta as 1 minus iota. Now of course it is your choice as to assume whichever function as 1 plus iota and whichever variable as 1 minus iota. It does not matter. Now what have they told us? That we have to find out the least value such that alpha by beta to the power n is 1. So what would my alpha by beta become? This would be my alpha by beta. This to the power n is equals to 1. So we need to find out the minimum value of n. So again, if you look at this expression here, 1 plus iota by 1 minus iota, what we first need to do is we need to remove the iota from the denominator. So I'll multiply the conjugate of it, which is 1 plus iota in the denominator and 1 plus iota in the numerator. And we did that earlier here as well. 1 plus iota upon 1 minus iota. What were we getting here? It was coming out to be iota, right? So this can be simply written as iota to the power n is equals to 1. So what is the least value of n for which I can get my iota to the power n as 1? Of course n needs to be 4 at least. So this becomes my answer. So this is the minimum value at which I can get my value of alpha by beta to the power n as 1. Now let's say if instead of this you would have, let's say, assumed that your alpha is 1 minus iota and your beta is 1 plus iota, still you would have gotten the same answer. Your alpha by beta would have become 1 minus iota upon 1 plus iota to the power n. So now what I'll do is, again I'll try to remove the iota from the denominator. So this would become 1 minus iota upon 1 plus iota into 1 minus iota upon 1 minus iota whole to the power n. So this would simply transform into 1 plus iota square minus 2 iota upon 1 minus iota square. So this simply becomes, this portion would cancel out amongst each other. We would have minus 2 iota by 2. So this would give us minus iota. So from here, what do we have? We would have minus iota to the power n as 1. So at what value of n we would get this to be 1? Of course it would be 4 again, because at 4 minus 1, since it is an even power, minus would become positive and iota to the power 4 is 1 at 4. So this is how we solve the question. Now talking about the algebraic expressions or algebraic functions of this complex numbers. Let's say we need to add or subtract two complex numbers z1 and z2. So simply what would be our method or way of adding them? We simply add the real number and we add the imaginary number separately. So addition of a plus iota b and c plus iota d would simply become a plus c plus b plus d iota. Subtraction also the same thing, the real numbers would be subtracted separately and our imaginary numbers would be subtracted separately. Now there are certain properties, of course the commutative properties applied here, which is z1 plus z2 would be equal to z2 plus z1. Associative properties there. Additive identity, again if I add 0 to my complex number it wouldn't make any changes. There is an additive inverse property as well. If I subtract the same complex number from my original complex number, it would give us 0 because the real numbers would be struck off and the imaginary numbers would also be struck off. So I would have 0. Now talking about their multiplication. Now simply multiplication can be done in the way how we used to multiply a variable and a constant. Let's say I used to have x minus 1 into, let's say, y plus 2. How I used to multiply this? First this term and this term, this term and this term, and then this one with this, and then this one with this. Similarly, that is the exact concept that we are going to use here. Let's say I have z1 and z2 as two complex numbers. I need to multiply them. So I can write it as a plus iota b and c plus iota d. And if I multiply them, first I'll multiply a and c, then a and iota d, then this, and then this. So I would get a into c plus a d into iota plus bc into iota plus, here I would have bd iota square. So this would, iota square would simply become minus 1. So I would have AC minus BD plus, if I take iota common, I would have AD plus BC here. So this is how I can separate my multiplication also in the real part and the imaginary part. Now again, the properties of multiplication are also similar. It follows the commutative, distributive, associative properties, and the multiplicative identity, which is z into 1, would always give us z. Now talking about division. Let's say if I'm dividing two complex numbers. Of course, if I'm dividing two complex numbers, then I am going to have a complex number in my denominator as well. And we do not prefer to have iota or any complex number in our denominator. We always want a real number only in our denominator. So it is our duty to remove it. So what we do is, let's say if we have a plus iota b upon c plus iota d. So we need to remove this complex number from the denominator. So what we do is, we write it as c minus iota d, c minus iota d. We multiply the numerator and denominator by the conjugate of the denominator. So from here, what are we going to get? This would become AC plus BD, and plus for iota I am going to have BC minus BD. Sorry, BC minus AD. And in the denominator, what am I going to have? C square minus iota square d square, and iota square is minus 1, so it would become plus d square. So this is how I remove numbers from my denominator, and this is what I'm getting. Now of course, this is the division that I'm getting. If I was to segregate the real part and the imaginary part in this division that I've gotten, so my real part of this z1 by z2 would become AC plus BD upon c square plus d square, and my imaginary part of this z1 by z2 would become BC minus AD upon c square by plus d square. So this is how I can segregate my real and imaginary parts in this function. And of course, when we talk about multiplicative inverse, let's say I have 1 by z, again I would have 1 by a plus iota b. Now I need to again multiply it by a minus iota b, the numerator and denominator both. From there I'll get this function. Now for division, one property that you need to remember is, let's say if I have z into 1 by z, what would this become? This can be written as 1. That means if I have equal complex numbers in the numerator and denominator, I can simply cancel them off and make my answer to be 1. Now this is an important property that you must remember, that complex numbers cannot be compared with each other. Again, complex numbers, it includes an imaginary part. That means overall it is an imaginary number. That means we do not know what that number is exactly, right? So we cannot compare it. That is why we cannot say that 3 plus 4 iota is greater than 2 plus 3 iota. This is never possible because we cannot compare two imaginary numbers, right? Because they are imaginary. We do not know how they would work or how are their properties. We are just assuming and we are trying to calculate things out of it. However, if let's say there are two complex numbers which are equal, we can equate those two complex numbers together. What we can do is, if we are, let's say if we are saying that these two are equal complex numbers, then my real part would be equal and my imaginary part would be equal separately. That means my A would be equal to C and B would be equal to D. Now talking about the conjugate and modulus, the conjugate of Z is equals to A plus iota B is Z bar as A minus iota B. So of course there is nothing new in this statement here. Now conjugate, there are a few ways of representing the conjugate. It can be represented by Z bar. It can also be represented by Z dash. So keep this thing in mind. And the modulus of Z is root under A square plus B square. Now what do I mean by this? Generally, if I say a complex number and if I try to represent it in a graph, it is represented as a point here. So this line here, this line is basically my Z, and this point here, this is X comma Y. Here, this is not my X axis anymore. This is actually my real axis and this is my imaginary axis. So here I'm going to have Y, and in my real axis I'm going to have the value X. So if I was to find out the modulus, that means I'm trying to find out the length from the origin. I'm trying to find out the distance from the origin. So how can I write it down? My height is Y, my base is X. So this can be found out using my Pythagoras theorem. So it would become root under X square plus Y square. So that is how I find out my modulus. This is what we call as the modulus. Now a few things that you need to remember about modulus, few key properties. First is, let's say if I have modulus Z is equals to 0. That means that my root under X square plus Y square is also equals to 0. Here I am considering that my Z is equals to X plus iota Y. So my root under X square plus Y square would also be equal to 0. Now, when can my X square and Y square be 0? Of course, when both of these together are 0. That means my X also has to be 0 and my Y also has to be 0. This means that my Z is basically 0. So keep this property in mind. Apart from that, let's say if I have modulus of Z, this would always be equal to the modulus of its conjugate as well. If I have, let's say, A plus iota B, I have A minus iota B. Of course, the modulus is going to be the same for both, right? Root under A square plus B square. The minus sign does not affect my modulus. So this modulus is going to be same. And let's say if I multiply my Z with Z bar, I'm going to get modulus Z whole square. You can, of course, prove this property as well. If I multiply Z and Z bar, I'm going to get A square minus iota B, iota square B square. So this basically becomes A square plus B square, which is nothing but my square of modulus Z. So this is what we get. A few more properties about modulus that you need to remember. Let's say if I have modulus of Z1 into Z2, this can be written as modulus Z1 into modulus Z2. Now these are few properties. Again, it is important for you to remember. Let's say if I have Z1 by Z2 in the division form, this can be written as Z1 upon modulus Z2. Another property, let's say if I have Z to the power n whole modulus, this can be written as Z modulus to the power n. So these are going to be the same things. Again, These are all, of course, all repetitive things you have already studied before. So this is basically just a revision for you all. Now let's look at this question here. This was a question that was asked in your previous year JEE Mains. Let u is equals to this, where z is x plus iota y and k is equals to 0. So k is a constant that has been given to us. If the curve represented by real value of this plus imaginary part of this is equals to 1, this intersects the y-axis at p and q. That means whatever curve is coming out from this equation, it cuts the y-axis at 2 points. Let's say if this is my curve, it is cutting the y-axis at 2 points p and q. That means if it is cutting the y-axis, let us assume this is my x-axis here, this is my y-axis here. Of course, what would be my x coordinate for these 2 points? It is going to be 0. This is going to be y1, this is going to be y2. So the distance between these 2 points would simply be y2 minus y1. That means my pq is nothing but modulus of y2 minus y1. So this value they've given us to be 5. Then we need to find out the value of k. So again, let us simply write down our z as x plus iota y and then segregate our real part aside and our imaginary part aside, and then we'll sum it up to get the value 1. So let's see, what do we get? U is equals to 2 times of x plus 2 iota y plus iota upon x plus iota y minus k iota. So from here, of course, first let us segregate the real and imaginary parts together. This would become 2x plus iota times of 2y plus 1, and below we would have x plus iota times of y minus k. Now again, it is our duty to remove the complex number from the denominator. So what we'll do is we'll multiply x minus iota times of y minus k and x minus iota times of y minus k in the numerator as well as the denominator. So from here, what do we get in the denominator? It is going to be x square. We would have minus of iota square y minus k square, and iota square is minus 1, so this would become plus y minus k whole square. And in the numerator, we are going to have 2x square. And what would be the other real part that we are going to get? We are going to get the real part by multiplying iota into 2y plus 1 into minus iota y minus k. So iota square simply becomes minus 1, so we would have plus 2y plus 1 into y minus k. And what would be our imaginary part? First we'll have an imaginary part by multiplying 2x with minus iota y minus k. So we would have minus 2x y minus k. And then our second one would be from 2y plus 1 into x plus x into 2y plus 1. So this is basically our u function that we are getting. So what is the real part here? In my u function, this portion here, this is basically my real part, and this portion here along with this is my imaginary part here. So let me segregate it out and add it to be 1. Let's take this to the next page. That means I have 2x square plus 2y plus 1 into y minus k upon x square plus y minus k whole square plus the imaginary part. Here I would have minus 2x into y minus k plus x times of 2y plus 1 2y plus 1 upon x square plus y minus k whole square. So this is my imaginary part and this is equals to 1. Now what they've told us, that this curve here that we've gotten just now, this curve cuts the y-axis at 2 points. That means if it is cutting the y-axis at 2 points. For those 2 points, what is my x coordinate going to be? My x coordinate would be 0. So let me simply just put x as 0 in this equation and find out my values of y that I'm getting. So if I put x as 0 in this equation, what would I get? This would become 2y plus 1 into y minus k upon y minus k whole square, plus here again I can take x common from both these terms, so this would become 0 and this is equals to 1. So if I try to cross multiply it and then I solve it, this would become 2y square minus 2yk plus y minus k is equals to y square plus k square minus 2yk. Minus 2yk to minus 2yk gets cancelled out amongst each other. This would become y square plus y plus minus k square is equals to 0. So this is a quadratic that we are getting. Now if I try to solve this quadratic, what would I get? Minus b plus minus root under b square minus 4ac. So this would become 4k plus 4k square upon 2a. So ultimately, what are the values of y from this equation that we can get? This 4k square plus 4k plus 1. 4k square, let me do that thing here. 4k square plus 4k plus 1. How can I write it down? This can simply be written as 2k plus 1 whole square. So this would become 4k square plus 4k plus 1. So if it is 2k plus 1 whole square, what would I have outside? It would become 2k plus 1 and minus 1 would get cancelled out for one case, and for the other case it would be added. So basically, what are the values of y that I would get? One would be k and the other value of y would be minus of 1 plus k. So these are the two values of y that I've gotten. That means in my PQ, my P point is 0 comma k and my Q point is 0 comma minus 1 plus k. Now they've told us that the distance between these 2 points is 5. That means modulus of k minus of, so this would become plus 1 plus k is equals to 5. So we have 2k plus 1 is equals to 5. So from here again we can have two values. So 2k plus 1 can either be equal to 5. From here we would get k to be 2, or 2k plus 1 would be equal to minus 5. So from here we would get our k to be minus 3. However, in the question they have already told us that k is greater than equal to 0. So if k is greater than equal to 0, this one would be rejected and this one is the value that we would take. So what is the value of k? We get it 2. And this is our answer. So I hope now the entire thing would have been pretty clear to you as to how we generally solve questions. Whenever we have an iota in our denominator, we simply multiply it with its conjugate to remove the iota from the denominator and then segregate our real part and our imaginary part.